In 2017, two neutron stars slammed into each other so hard they shook the fabric of space and time. It made headlines for weeks. Then, like most cosmic events, it faded from the news cycle. But that same collision just got dragged back into the biggest argument in modern cosmology, and this time it's taking a side. For over a decade, two completely different ways of measuring how fast the universe is expanding have refused to agree with each other. One method says the universe is expanding a little slower, and the other says it's expanding noticeably faster. Both are precise, but both can't be right. This year, a team went back to that old neutron star wreck with sharper tools than anyone had back in 2017, and they pulled out a number that might finally break this tie. And strangely, the newest evidence in cosmology's oldest fight comes from data almost a decade old. Here's the fight. Astronomers call it the Hubble tension, and it comes down to a single number, the Hubble constant. Think of it as the universe's current speed limit for expansion, how fast every stretch of empty space is growing right now. There are two main ways to measure it, and they come at it from opposite ends of cosmic history. The first reads the early universe, using the cosmic microwave background, which is essentially the leftover glow from a few 100,000 years after the Big Bang. That ancient light isn't perfectly smooth. It's freckled with faint hot and cold spots, and those spots have a characteristic size, set by waves rippling through the hot plasma of the infant universe. The clever part? Physics tells us how big those ripples actually were. So we measure how big they look on the sky today, compared that to their true size, and the geometry hands us with the expansion rate. In this case, about 67 kilometers per second per megaparsec. Call this the early universe answer. One quick note on units. 67 is shorthand for 67 kilometers per second per megaparsec, the metric I just mentioned. The farther out you look, the faster space stretches. Just to shorten it, from here on out, I'll just say the bare number, 67. The second method ignores the Big Bang and measures the nearby present-day universe, one rung at a time, which is why it's called the cosmic distance ladder. For the nearest stars, distance is pure geometry. As Earth orbits the Sun, they shift a hair, and that shift gives their distance. Some of those stars are Cepheid variable stars, which pulse at a rate locked to their true brightness, so once geometry pins down a few, you know how luminous every Cepheid actually is. Find them in a distant galaxy, and how faint they look tells you how far that galaxy sits. Some of those galaxies also host type 1a supernovae, exploding white dwarfs that all peak at nearly the same brightness, bright enough to see across the universe. Each rung calibrates the next, out to galaxies far enough that cosmic expansion is visibly carrying them away. Compare their distance to how fast they're fleeing, and you land at around 73. This is the late universe answer. Both camps keep rerunning their numbers and only growing more confident in their results. And they still don't agree, which leaves us with only two possibilities. Either one of these methods has a hidden mistake buried inside it, or our physics itself is missing something about how the universe works. Which of those it turns out to be is the entire ballgame. And for over a decade, both sides have both dared a third, independent method to walk in and break the tie. Because this isn't just trivia. That one number sets the age of the universe, the cosmic distance scale, and how much dark energy is out there stretching that space apart. Get the Hubble constant wrong, and a surprising amount of cosmology quietly tilts with it. So how does a single collision from 2017 weigh in on a fight that's stumped the world's best telescopes? Because a neutron star merger gives you something neither of the first two methods have: a completely independent yardstick. When two neutron stars collide, they don't just ripple spacetime. They also fire a narrow jet of particles that are traveling nearly at the speed of light. And the gravitational waves from the crash already carry a distance baked in. The farther away the merger, the weaker the signal. So in principle, you read the distance straight off of that wave. Except there's still a catch. That signal's strength doesn't only depend on distance, it also depends on the angle we're viewing the collision from. And the two are tangled together. A nearby merger, seen edge-on, can fake almost the same signal as a farther one seen face-on. Until you know the angle, the distance stays fuzzy. That's the knot that hobbled the first attempt. And that's exactly what the jet is for. Over the months after the crash, radio telescopes watched its glowing tip crawl across the sky, appearing to move faster than light, a projection trick that only happens when a jet points almost, but not quite, at you. How fast it seems to move pins down the viewing angle. Feed that angle back into the gravitational wave signal, and the distance angle knot comes undone, leaving a very clean distance to the merger. Pair that with how fast the merger's home galaxy is drifting away, and you've measured the expansion rate directly. No ladder, no microwave background, just Einstein's equations and a moving radio dot. But here's the question a sharp viewer's already asking. This merger happened in 2017, so why only now? Because that first attempt barely constrained the viewing angle, and the error bars were enormous. Since then, radio astronomers kept imaging the afterglow for months, watching the jet crawl across the sky in ever finer detail. This new study pulled together nearly a year of that radio data. Observations spread across a global network of radio dishes in the US and Europe, known as the High Sensitivity Array, plus Hubble's own tracking of the afterglow's position. And then they reran the geometry with a far more rigorous statistical model than anyone had used before. The result? A viewing angle narrowed to between about 17 and 19 degrees, and a distance to the merger accurate to within a few percent. Same collision, but dramatically sharper ruler. So, what did they actually get? Well, they calculated a Hubble constant of 65.5, give or take about 4.4. And to do a quick gut check on that number, because gravitational wave Hubble constant has a track record of being a moving target. The very first attempt at this, right after the 2017 merger, gave a value of around 74, but the error bars were so wide, plus 16, minus 8, that it couldn't rule out much of anything. A 2019 follow-up to this calculation, using earlier radio imaging of the same jet, tightened that to around 70.3, give or take about 5. This new number, 65.5 plus or minus 4.4, is a modest step up in precision from that 2019 result. But the real story isn't the error bar, it's where the number ultimately landed. Compare it to the two established camps we discussed earlier. The early universe answer sits near 67, precise to about 1%, and the late universe answer sits near 73, precise to about 2%. This new measurement is only precise to around 7%, so don't crown it champion on accuracy alone. It's still the roughest of the three. But look at where it landed. This method, using a nearby merger, not the ancient afterglow of the Big Bang, is by every definition a late universe technique. That kind of method that should land near 73, next to the supernovae. Instead, it landed within half a standard deviation of the early universe answer, and nearly 2 full standard deviations away from its own late universe neighborhood. That's the twist. A late universe road just showed us a number that's closer to the early universe destination. And the team's lead researcher put it plainly. This makes it less likely that both existing answers are somehow secretly correct at once, propped up by some undiscovered piece of physics. If that idea were right, this new measurement had every reason to land somewhere in between, but it didn't. So, does this settle the Hubble tension? No. And the researchers are the first to say so. One merger with error bars still wider than either camps doesn't overturn a decade of precision cosmology, but it does shift the weight of evidence in favor of one of the answers. Before this, gravitational wave measurements were too imprecise to favor either side. This one is the sharpest one yet, and it's not neutral. It's definitely leaning toward the early universe camp, the one anchored in the Big Bang's afterglow. And that matters, because remember those two possibilities from the start, a hidden mistake or missing physics? This is where they cash out. If the answer had come in at 73, that would have been the earth-shaking one. It would mean that our standard model of the universe is missing something fundamental. To explain it, cosmologists have floated exotic fixes, such as a burst of so-called early dark energy or extra kinds of particles that we don't know about yet. Anything that lets both numbers be right at once. New physics, essentially. That idea is still very much on the table, but a little less likely now. But if the true value clusters near 67, where this one actually landed, that exotic menu becomes a lot less necessary. The standard model probably stands, and the disagreement starts looking less like broken physics and more like a subtle measurement error hiding in the local distance ladder, quite possibly in how we calibrate those supernovae. Less, the universe is stranger than we thought, and more, one of our rulers is slightly off, which would be its own kind of relief and a very specific place to start looking. And this isn't a one-shot result. Every future merger caught with a well-aimed jet and enough radio dishes watching adds another independent vote. Here's the testable part. If this measurement is a preview and not a fluke, the next handful of well-observed mergers should keep clustering down near 65 to 67, not up near that 73 number. That's a specific, checkable prediction, and with detectors improving every run, we won't have to wait another decade to test it. Two roads that have disagreed for over 10 years just had a third traveler show up at the crossroads. And when you ask her which way she came from, she points back toward the early universe road. So that about does it for today's story. I'll link the paper and the press release below if you want to dig into the jet fitting model yourself. It's a genuinely clever piece of geometry. If this channel has helped you make any sense of that, please consider subscribing. There's a lot more Hubble tension coverage where this came from. And I'll leave you with a quick question for the comments. If you had to bet everything on one side of the Hubble tension question right now, early universe or late universe, which way are you leaning and why? Until next time, this has been Uphillian. Thank you for watching.